Kia ora. My name is Bill Trompetter, and I would like to give you a short presentation of about 13 slides on a paper that I've written recently entitled The Electromagnetic Angular Momentum of an Orbiting Charge. To illustrate that, this will be talking about a hydrogen atom where the electron is orbiting the proton. To set the scene, I'd like to get you to just briefly think of three questions I'd like to pose to you. The first being is that electrons are usually thought of as point particles, but is this really the case? We know that charges have extended electric fields which emanate from the charge. So how does this affect the inertia and the angular momentum of an electron? And the third thing I'd just like you to briefly think about is what is the difference between what we see in the lab frame versus what the proton sees versus what the electron will see? It will depend on our perspective as to what we see. And this is indeed what happens from the various interactions shown below, that these different interactions are from different perspectives of what is happening in the hydrogen atom. And we're going to talk about this in more detail. So, and we're also, essentially, this presentation is about bringing three pieces of knowledge together to make a fourth. The first piece of knowledge will be that the electron inertia is due to the electromagnetic mass. The second will be that the electron spin is synchronized to the orbital motion. And the third piece of knowledge we'll bring to the fore is that the electric field lines are curved in the electron's rotating frame of reference. And we'll combine these pieces of knowledge to investigate how the extended electromagnetic model for an electron can be used to derive the spin-orbit interaction and corresponding orbital velocity to get a surprising and very interesting result. So the first piece of knowledge is around that the electrons have electromagnetic mass. We know that a charge has an electric field. We know that electric fields have electric field energy density. And we know from special relativity that energy is equivalent to mass. So therefore, electrons will have an extended electromagnetic mass distribution, and that this will therefore influence the inertia when the electron comes to rotate for any rotational motion, and it will also influence the angular momentum. The second piece of knowledge we're bringing is that the electron spin is synchronized to the orbital motion. We know that the electric field will have a gradient from the proton extending outwards, and the electron will see this in its orbital motion. And this will act to encourage and indeed make the electron orientate its orientation towards the central charge. And this is confirmed by the spin-orbit interaction, where the orbital electrons align their spins to the central nucleus, either parallel or anti-parallel. And this is analogous to what we see in astronomical bodies, where the gravitational gradient leads to tidal locking and synchronous rotation of orbital bodies. And we know this to be true for, in the case of our moon, we only ever see the one side of the moon is always orientated towards us. And this is indeed true for satellites and moons and of other planets as well, that that the gravitational gradient acts to make the orbital body orientate towards the central mass. So given that electron spin is synchronized to the orbital motion, we don't expect to see any independent spin. That will only come if there's an independent motion or independent spin of that orbital body. And this would come or could come from precession, such as the spin-orbit interaction or the Thomas precession interaction. And so this is where we would expect to see the effect of the electromagnetic inertia of that orbital body making an influence. So this is what we're going to investigate shortly. And when there is rotational motion, so first of all, we want to also talk about what happens in the rotating frame. We know that in the lab frame of reference, that the projectiles will emanate with straight radial trajectories. Is assuming that they're not acted upon by other forces. However, in a rotating frame of reference, that's not. We see that they take on a curved trajectory, and that is illustrated in the top graphic there, where a ball bearing starts off in the center of a turntable and makes its way to the outside of the turntable. You can see that in the lab frame, which is the top picture, part of it is that it takes a straight trajectory, whereas in the bottom frame, part of the image, it's in the rotating frame of reference, and you can see that it takes on a curved trajectory. The bottom YouTube clip, which will start shortly, will show a cannonball on a rotating turntable. And this cannon is firing cannonballs, and you can see that as they leave the cannon, they take straight trajectories in the lab frame of reference. Now we're going to switch to the cannon, rotate with the cannon, and you will see that now when we rotate with the cannonballs are taking on curved trajectories. And so let's now look at what happens for electric field lines. Again, for a stationary charge, the electric fields are radial and straight. And indeed, also, this is in the lab frame. And indeed, for a moving charge in the lab frame, the electric field lines are also radial and straight. We know from relativity theory that the electric field lines can be changed as viewed for a moving charge in the lab frame. The electric field line in the same orientation as the velocity remains the same. However, electric field lines in the perpendicular direction to the velocity are changed by relativistic transformation. However, there's also a magnetic field. However, the net electromagnetic field density remains the same. So the net for a moving charge means the same as the charge at rest. What does change is that there is a time dilation, and there is also a relativistic length contraction. And so that these add up together to transform the volume into which the electromagnetic energy density extends. However, what we're really interested in is what happens in the rotating frame for the electric fields. And in the relativistic, when relativity is taken into account for the rotating, in the rotating frame, the trajectories actually take on, become circular, and they exhibit a maximum radius to which they can extend. And this radius is where the tangential velocity approaches the speed of light. And I've also shown here the other transformation of other variables that are happening in the rotating frame of reference. So, as I mentioned earlier, we are interested in what the spin-orbit interactions for the charge. And first of all, we'll look at what happens based on the literature for a point particle. Lamore calculated the spin-orbit interaction based on the magnetic field that the electron would see, and so that that's on the top equation there. But what was found was that this was twice as large as what was observed experimentally. And then Thomas came along and showed that there needed to be a relativistic correction to this, to take this center of mass Lamore energy equation to correct that for what we would expect in the lab frame. And so what we actually see in the lab frame is an electric dipole and interaction. And that is depicted by there's the third equation there and the far right graphic. So up until this point, this is all from the literature. This is what we, so there's nothing new here. What I've now in the paper is, and what I'd like to show now is that we need to incorporate electromagnetic, extended electromagnetic mass of the charge into these equations, and so for the Thomas precession and the electric dipole interaction, they, as I've showed earlier, that they were based in the lab frame. So these, the electric fields for these interactions are still radial and straight. So these will transform. So when we consider the extended electromagnetic mass of the electron, these will still have the same interaction terms as for a point particle. So these remain, those equations remain the same. What does transform is the Lamore precession, because this is calculated in the electron's center of mass rotating frame of reference. And as we've shown before earlier, in the rotating frame of reference, the electric field lines take on curved trajectories. So this is the equation which changes when we consider an extended electromagnetic particle. And that is the equation that we get is that equation in the bottom part of the slide. And you can see that that is actually different to what was obtained for a point particle. However, and then what we need to do to that is to still add in the Thomas correction, which is in the red equation there, and then we can compare that with the electric dipole term, which is the same as the point particle equation. And these can be compared, either the equations can be compared directly, or I've plotted them in the graph on the plot there. And what we find is that the energy needs to be conserved from each of these perspectives. One of the requirements for special relativity is that the energies are conserved between the different frames of reference or an agreement. And we can see that this only occurs when the velocity is at a specific value, and that specific value is 1/136.97 times the speed of light. So this value, or that velocity, is equivalent to the fine structure constant, and this turns out to be 99.95% of the experimentally determined value. And indeed, this also is effectively deriving an expression for the Planck's constant, because that is related to the fine structure constant. So this theory presented here, and indeed in the paper, is to basically, at a first order approximation, there are more refinements that could be done to this model, and I believe can achieve even closer agreement. In our calculation, in Lamore's equation, it was a G factor of 2 was arbitrarily, or was assumed. It was this was added as to make the theory fit the experimental results. In this approach, I have not used a G factor of 2. It was not needed. So this shows that the classical electromagnetism correctly describes the spin angular momentum. And since basically I'm using a G factor of 1, this is implying, that when we look at the actual precession, the Lamore precession with the Thomas precession, we actually get equal and opposite terms for these precession frequencies, which means that there is no net precession in the lab frame. And this makes sense, because in the lab frame, we see an electric dipole, and the electric dipole in the electric field will act to align it and not to make it precess. So this makes good sense. And so hopefully, so the outcome is basically that these results reveal the surprising result that the fine structure constant and Planck's constant are a natural extension of classical electromagnetism, and that quantization of angular momentum is a consequence of energy conservation for electrons in orbits with synchronous rotation. So a surprising result, but hopefully an exciting one too. So yeah, I hope you found that useful.